Welcome back to the course on Fundamentals of Artificial Intelligence. We do the second module from today. The module is called Problem Solving by Search. First, we will look at what is that makes AI programming different from general computational paradigms. We will look at what is commonly called an AI technique, and then introduce production systems, a system of programming which captures the essence of AI systems. We will focus on what are the different components of a production system, and then looked at some specialized production systems. This is what the overview of the course today looks like. We would first talk on what is an AI technique. How is AI different from the general traditional programming? What makes AI programming different? At the end of this course today, you should be able to identify what is production systems, the components of a production system. We would introduce the basic procedure and look at different control and control strategies. Production systems is what separates facts, the way reasoning happens, and the control system into three distinct units. We shall look at each of them very closely and then focus our attention on how control and control strategies are designed. We will look at what is called irrevocable control strategy, backtracking, and graph search. A very interesting way of looking at things as a production system involves not only looking at these three units, but also able to do what is called problem reduction. We will look at a very specialized production system called decomposable production system, which allows us to reduce the problem. And we will also look at something called the commutative production system. But then first, let us focus our attention on what is an AI technique. Artificial intelligence, as you can remember from the first lecture of module 1, involves problems that span a very broad spectrum. Now, they are problems like natural language processing, navigation for robot in a clustered environment. It could be like autonomous driving or automated reasoning. They appear to have very little in common, except that they are very hard. The focus when we ask the question, what is an AI technique, is to look for an answer if there are any techniques that are appropriate for the solution of a variety of these problems. Is there something common which is there for all these problems that appear? One of the few hard and fast results to come out of the first 3 decades of AI research is the fact that any such intelligent program that one needs to write requires knowledge. This is a very interesting idea, that knowledge, if you have to have in a program, that can give rise to intelligence. AI technique, therefore, is a method that exploits knowledge and should be represented in such a way that this knowledge that we are talking of captures generalization. Here it is very important for us to note what we mean by generalization. Whenever we are talking of a technique that exploits AI, we are more interested in capturing the general information about the problem rather than capturing very specific things of the problem. The next important thing that an AI technique exploits is a knowledge that is understood by the people who provide it. Another important characteristic is that this knowledge that's provided needs to be easily modified. When I say knowledge needs to be easily modified, what I mean is that the knowledge needs to be worked on by some system to create new knowledge. And these new knowledge that I create out of existing knowledge should be able to be created by very simple operations. This, I think, is what drives AI technique, and an AI technique is therefore these three things used to help overcome the sheer bulk that is required. What is an AI technique? In order to answer this question, we need to understand that the aim here is to build a system, definitely for a particular problem, but then the solution that we expect is as generic as possible. So we are looking for a generic solution to definitely a particular problem, and when we want this, we need to do four things. A, we need to define the problem precisely. Problem definition is as important as what knowledge we capture for that problem. The second thing that needs is a great analysis of the problem. One needs to understand what this problem that we are trying to tackle is about. Number three, we need to isolate and represent the task knowledge. Now, what is task knowledge and how do we isolate and represent task knowledge is something that we will look at in the next few examples that we are going to talk about. The fourth interesting thing is then, given these three important things, that we define the problem precisely, we analyze the problem, we then represent the task knowledge. The onus is now to choose the best problem solving technique. It is therefore important for us to realize what is the basic difference between traditional programming and programming with artificial intelligence, or programming that tries to create AI systems. Traditional programming is when we program and look for answer for only a specific question it's meant to solve. Like, let's take an example that I'm interested in finding out the square root of a quadratic equation. My focus is only on getting the roots of the equation. Whereas if I am doing programming with AI, the idea is to get answers to generic questions rather than only specific questions that I am asking. Like here, one could take the example of playing a game of checkers or playing a game of chess, or more interestingly what we will exploit is a game of what we call 8 puzzle, where I have 9 tiles positions and one of the tile position is free so that I can move it around. And given a start position of that configuration of tiles, I want to look for a goal position of the configuration of tiles. And when I am trying to look at a solution of this, I am not interested in a specific solution of given a particular start state to a particular goal state. I am interested in a way of arriving at from any given start state to any given goal state. The second important difference is that any traditional programming paradigm that we exploit, modification in the program itself will lead to change in its structure. Whereas if it is an AI programming paradigm, which we will look at today, modifications in program do not change the structure. This is because, as we will look at the paradigm of programming called production systems, which captures the essence of AI systems. It is made up of independent pieces of information. The rules, facts, the reasoning and the control are completely distinct elements. Therefore, modifications in one of them do not change the other or do not change the structure of the program. The third interesting difference, therefore, flows from the second. Modification in traditional programming may lead to adversely affecting the program. Whereas, here when I am talking of a production system, or what I loosely refer to as programming within AI, modifications could be quick and easy. So, we are in now position to state what we started our lecture with, that we want to do problem solving as search. But before that, we need to understand what do we mean by problems as a state space search. Problem solving task within such a module can be formulated as search in state space. A state space consists of all states of the domain and states of operators that change one state into another. The states can best thought of to be as nodes in a connected graph and operators as edges. And when we were looking at problem solving can be formulated as a search in the state space. Let's look at this example more clearly to understand what we mean by this. So, let us say we have taken problem to find out the solution of an 8 puzzle game. An 8 puzzle game has a 3 cross 3 matrix where numbers are written 1, 2, 3, 4, 5, possibly 6, 7, 8, with one of the tile which is unoccupied, so that you can move that tile. So, this space can come here and here. So, basically when I am talking of the 8 puzzle itself, I can have such configurations, and such configurations can change from one to another by a set of operators which happens because of movement of the empty tile. Like here, I could take the empty one to the right. So, 5 comes here and I have 1, 2, 3, 5, 4, 7, 6, 8. So, from here to this state here, I can come by a simple operator which would be something like take the empty to the right. And when I am doing this, I am generating a number of newer states. That newer states that is generating is all of them together creating what is called the state space. So, all of these states of the domain and all of these operators that I have. So, we could have 4 operators where the blank goes to the right, the blank could be pushed to the left, the blank space could be pushed up, or the blank space could be pushed down. All these operators generate what is called the set of operators. The states of the domain and the set of operators, once defined, I can think of moving from one state to the other state. And basically, what we will have is therefore, given a state, some way to move through new states, to new states down there. And when I am looking for a solution to this problem, okay, given a start state S and some goal state G, the solution to this problem is about finding a path from S to G. So, path from an initial state to a goal state, if it is found, the problem is said to be solved. This is essentially what it means to solve problems as state space search. The set of all possible configurations that I get of the relevant objects is the state space of the problem. This is also referred to as the problem space. I showed you an example of the 8 puzzle. So each tile configuration that I had drawn in the previous slide, like this 3 cross 3 matrix with numbers running from 1, 2, 3, 4, 5, 6, 7 and an 8 with one of them as empty is a problem state. 8 puzzle actually has a very relatively small problem space, which is some 9 factorial different configurations. So when we are looking for a solution from a given start to some given goal position G, which could be any other configuration in the system, like I could be thinking of arranging them as 1, 2, 3, 4, 5, 6, 7 and 8. I am thinking of getting a way to come from this to this, and this total configurations that are there is only 9 factorial different configurations. So such a search would be possible. We can think of another example, which is about the game of chess. Initial state for a game of chess could be thought of as 8 cross 8 array. The legal moves a set of rules, each rule consisting of 2 parts, a left side that serves as pattern to be matched and a right side that describes the change to reflect the move. Goal state could be any board position where the opponent does not have any more legal move, and therefore it's a win. When we start playing chess by starting at an initial state using a set of rules to move from one state to another, we end up in one of the set of final states. This state space representation seems natural for games such as chess, 8 puzzle, because the set of states corresponding to set of board's position. This kind of representation may not be very obvious, but is also useful for less structured problems with use of more complex structures than a matrix. I would like to emphasize here that the game that I have spoken of, 8 puzzle, the matrix representation came obviously to the mind because we were talking of a 3 cross 3 arrangement of tiles. For chess, an 8 cross 8 matrix immediately comes to mind. But then this kind of state space representation is also useful for other less structured problems. The only emphasis that I want to give here is now to point out that under less structured problems, if we want to use such a state space representation, we would need more complex structures than a matrix. And such a representation, such a mode of problem solving could be useful. Now here is the formal description of a problem. So what we have is number 1, the state space. The state space define all possible configurations of the relevant objects. The number 2, what we have is the initial state. The initial state specify one or more states within that space as the possible situation from which problem solving can start. Thereafter, we have the goal state. The goal state specifies one or more states that would be acceptable as solutions to the problem. And of course, this is about only the different configurations of states that we are talking of. Together with it, we would need a set of rules that describes how we are going to move from one state to the other state. So these are called operators. So here is the formal description of problem solving a state space search. We have to define the state space, which is all the possible configurations. We then identify one or more states within the space as possible situations from which we can start. That's the initial state. One or more states from the problem space that is acceptable as solutions is referred to as the goal states. And then a couple of rules that describe actions available. Now, I will just take 1 minute to again emphasize what we were talking of as operators. Operators have two interesting portions, one on the left and one on the right. Information must be true. Everything on the left must match so that I can take that particular operation so that we have information on the right to be true. Like remember our 8 puzzle game where we had this 9 tiles and we had a rule which said like an empty can go to the right. This rule is applicable in the above state because let's say we have 5 here, the empty moves to the right, then I have a configuration that leads to other things remaining same, 5 coming here and empty here. Whereas the same operator from this group of operators, if I take another which said move to the left, empty, this is not applicable in this state because here I cannot move to the left. So when I specify the set of rules that describes actions or operators, information what must be true for the action to take place needs to be looked at first, and then the action can take place and can generate new information as we have seen here. So let's look at playing 8 puzzle with problem solving a state space. So here is our start state where I have 9 tiles and my empty at the bottom, and this is my goal state where I have arranged everything as 1, 2, 3, 4, 5, 6, 7, 8 with empty at the middle. Now as I go on generating, and remember the 4 operators that we were talking of, let's quickly recall our operators. So we could have empty that moves to the right, we could have an empty that moves to the left, we could have an empty or vacant tile position and that vacant tile position that moves up and a vacant tile position that moves down. Given this start state S and given the goal state G and these 4 operators that we have here, let us try to understand problem solving as state space search. So at this point, of the 4 operators that I had highlighted in the previous slide, 3 positions are possible. The empty could go up, the empty could go left, or the empty could go right. So these are the 3 configurations that can be arrived at from the given set of the given start position. I then look at these new configurations and look at my 4 operators that I had highlighted in the previous slide and try to employ these operators here. So I will take each of them one by one. Now we generate new states from here. So one could come to the center and the other position that I could generate is that 8 could come down, and here is the third position where 4 could come to the center. To just keep my discussion of these 8 puzzle problems shorter, I have taken a route that is taking me towards the goal, but that does in no way stops us from exploring this path as well. Just to highlight that we can arrive at this goal very quickly given this. So, I have just looked at this path. So, then next I generate the two positions. One, these empty can go to the left and the empty can go to the right. So, I have two positions. I now highlight it and see what happens when operator applies on these positions that I have marked here. So, once I have that, I can have a location like one could only go up. If it goes to the left, I generate something which has already been generated. So, I do not do that, and what I get after a couple of steps is my goal position. So, what I want to emphasize here is that starting from a start position and which was part of a space of the problem states, which we have seen is factorial 9 factorial, we could go and look at different configurations on the way, generating a lot of them, and arrived at the goal position G from a start position S. So, this paradigm of working like this is problem solving as state space search.